Hello, these are the solutions to quiz 16. A compound has a molecular weight 4 times its empirical formula, and it has a composition of 88% by mass carbon and 11.2% hydrogen by mass. What is the molecular formula? Okay, so what we might do here is take the 88.2 grams of carbon over to moles, likewise 11.2 grams of hydrogen over to moles. Use the molar mass of carbon. Mole of carbon is 12.01 grams. 1 mole of H is 1.008 grams. If we do these calculations here, we get 88.2 divided by 12.01 is 7.34 moles. Present in a ratio to 11.2 divided by 1.008 to 11.11 moles of hydrogen. The carbon is smaller, so I'll do 11.11 divided by 7.34. That works out to 1.5. So if we divide both of these by the smaller, where x is the smaller of the two numbers, we get 1 mole of carbon present to every 1.5 moles of hydrogen, leading to an empirical formula of C2H3. And so then the molecular weight is 4 times the empirical formula mass, so we're going to be C8H12. So C8H12 is what we end up with for number 1. Number 2, compound is XCl3, X is unknown. If the compound contains 79.8 chlorine by mass, what is the atomic weight and identity of X? So the nature of this particular problem is that we might be able to identify and say, okay, whatever the atomic weight is of X, so the atomic weight of X, divide by the formula weight of the compound, times 100% is the definition of the percent X in the compound. So this would be the percent X, and we know what that is. The percent of X would just be the difference of the chlorine mass in 100%, so this would be 20.2%. So we know what this is. This is the percent X is equal to whatever the atomic weight is of X times just the 1X in the formula, because of what we know about the compound divided by the formula weight. Now the problem is I don't know this or this. Like I don't know either the atomic weight of X or the formula weight at this point. So what I might do is say, well, I could get the formula weight if I do 3 times the chlorine mass, divide by the formula weight, that this is the percent chlorine of the compound, which we know times 100% is 0.7, is 79.8. I'm going to get rid of the percent and say the fraction of chlorine in the molecule is just the fraction 0.798. So if I take 3 times 35.453 and divide that quantity by 0.798, that tells me that the formula weight of the compound is 133.2. So if I know there's 3 chlorines, and I know their mass, and I know the percent chlorine by mass, I can work out the formula weight of the compound as 133.2 AMU. And then I can feed this back in over here, and then solve for the atomic weight of X. Okay, so I know that the atomic, and if I get rid of this as a percent, express it as a fraction, 0.202 is the fraction of the compound that's X. So I take 133.2 times 0.202. That should reveal the atomic weight of X. So it comes out to be 26.9 AMU. When I take the formula weight times the percent that's X, and we get that this is aluminum. So it's aluminum chloride, AlCl3. From the balanced formula, we get CO2 and water by the combustion of glucose. So from the balanced combustion reaction of glucose, how many grams of CO2 may form when 10.5 grams of glucose combusts with excess oxygen? So we're just taking C6H12O6, given as glucose, that this is reacting with O2 to form CO2 and water. Get a little bit of room here. Okay, and so then, not leaving enough space to write in the coefficients here, so plus H2O, we're going to need 6 to balance the hydrogens, then we're going to need 6 to balance the carbons, then we're going to need 6 plus These six, you might picture these six O's being these six O's here, and then needing six O2s to put us in the balance. So 1 glucose plus 6 O2 go to 6 CO2 plus water. And so if we want to know the number of grams of CO2 that form, that's what we're looking for. We're starting with the combustion of 10.5 grams of glucose. We're given the molar mass in the problem, 180.2 grams per mole of glucose. 1 mole of glucose produces 6 moles of CO2. 1 mole of CO2 has a molar mass of 44.01 grams. So if we do this, 10.5 divide by 180, so 10.5 divide by 180.2, then we have 0.05826 moles of glucose present. We produce 6 times that in CO2, so we make about 0.35 moles of CO2, and 0.35 moles of CO2 would be about a little over a third, so 15.4 grams is what we end up with here for this one. So moving on to number 4, when 1.6 moles of sodium and half a mole of oxygen react by the below reaction, which reactant is present in excess and how much of it remains following the reaction. This might not be a bad one for a BCA chart. So what we have present before is 1.6 moles, 1.60 moles here. I like to do BCA chart with moles, not grams. Not that you can't do it with grams, but I like to think of the reacting units moles. So we have half a mole of O2 and then initially none of the sodium oxide. And so the question here is, which of these goes to 0? So I do a minus 4x, a minus x, and these then subtract off to either what's left over or to 0. Let's pick the one that's wrong first. If this goes to 0, then x is equal to half a mole. Then I'm going to lose 4 times half a mole in the case of sodium. That would mean that we have negative 0.4 moles of sodium present. We can't have a negative quantity, so that makes these incorrect. So we're going to go to 0 on sodium and have some of the oxygen left over as the excess reactant. Okay, so if I lose all of the sodium, then my x is equal to 0.4. So I lose 0.4 moles of the oxygen. So 0.4 moles removed leaves me with 0.10 moles of O2 present once the reaction completes. So which reagent is present in excess? That's O2, and half a mole remains. 0.4 moles is consumed. 0.1 mole remains. Okay, now you could think of this a few different ways too, that if we, the amount of O2 that we need to react with 1.60 moles of sodium, you just use the coefficient 4 moles of sodium, react with, and when they react, they require 1 mole of O2 to be present. So the number of moles of O2 that react would be equal to 0.40 moles. And then that's what reacts. If you had half a mole present, then you just have to carry out this subtraction to get the 0.1 moles. So you can just use dimensional analysis too, but you just have to kind of at least think through what a BCA chart is trying to show at the very least to get a problem like this correct. So number 5, when 1.2 moles of carbon reacts with 1.4 moles of oxygen by the below reaction, 0.78 moles of CO2 forms. What is the percent yield of the reaction? Okay, now here this reaction is balanced 1 to 1 to 1. So oxygen is present in excess, so carbon is the limiting reactant. You usually have to identify the limiting reactant so I know which reactant to use to work out the theoretical yield. So the maximum yield of CO2 should be 1.2 moles. So this, once we have stoichiometry kind of down, we can say, well, carbon, if it reacts fully, makes 1.2 moles, oxygen will make 1.4 moles, so 1.2 is the maximum moles of the CO2 that can be formed. So our percent yield should just be 0.78 divided by 1.2, that's 65% in terms of the yield. So then when we have a 1 gram sample of a compound of CHNO, combust with oxygen, we make this many moles of CO2, this many moles of water, and we're asked the empirical formula of the compound. Now, this is a tiny twist. It's actually a slightly easier twist because we're just being directly told the moles of CO2 and the moles of water instead of the mass of CO2 and the mass of water. So the question is still really how many grams of carbon are there, how many grams of hydrogen are there. I'm going to work these out without showing the arithmetic because I'm just going to take 0.0526 moles of CO2 contains a mole of carbon. A mole of carbon is 12.01 grams. So this is 0.632 grams of carbon. And then likewise for hydrogen, if I have 0.0438 moles of water, I have 2 moles of hydrogen. So I'm going to double those number of moles and then multiply by 1.008 the molar mass of one H atom, or of just simply hydrogen. So that's 0.0883 grams of hydrogen. So then we have a 1 gram sample. This third element, which is oxygen, the number of grams of O, is just our sample mass, 1 gram minus 0.0883 minus 0.632, leaving behind 0.280 grams of O. So we have a ratio of our 3 elements to each other, of the C to H to O. I just need to convert those over to moles and then get a simple whole number ratio. And so if I go moles here, carbon to hydrogen to oxygen, 0.632 divided by 12.01 is 0.0526. The moles of hydrogen, 0.0883 divided by 1.008 comes out to 0.0876 moles of hydrogen. And then oxygen, 0.28 divided by 280 divided by 16 is 0.0175 moles of O. And then which of those is the smallest? Looks like the O. So we'll divide all of them by X, where X is equal to the number of moles of oxygen. So divide all of them by 0.075. So 0.0526 divided by 0.0175 works out to 3. So this is our actual moles in these samples. This is our whole numbers, or close to whole numbers. It's our attempt to determine whole numbers. 3 moles of carbon, 0.0876 divided by 0.0175 comes out to 5 moles of hydrogen to 1 mole of oxygen, of course. So our formula should be C3H5O. Moving on. Molar mass of Valium. If this number of moles has a mass of this. So if you know the moles of a compound and you know how much mass it contains, then you can calculate the number of grams per mole. The number of grams per the number of moles is the definition of molar mass. Okay, so it's just the idea of molar mass. So 24.37 divided by 0.08560 moles grams. So 24.37 divided by 0.08560. So 284.7 grams per mole. How many carbon atoms are present in 25 mils of ethanol? And we're given a density here. Okay, density gets us from milliliters or volume to grams. We use a molar mass to get the moles, Avogadro's number to get to molecules, the formula to get to the carbon atoms. So number of C atoms equals 25.0 mLs times 0.7893 grams per ml. So the volume cancels. So that's the mass of the sample. The molar mass is also given 46.07. A lot of times you're given the molar mass to speed up the problem, so you don't have to spend your time calculating the molar mass. So that's the moles of ethanol. And then 1 mole of ethanol contains 6.022 times 10 to the 23 molecules of ethanol. Ethanol molecules. I'm going to do C2H6O molecules. And then 1 molecule of ethanol of C2H6O obviously contains 2 C atoms. So we go 25 times the density. If we stop calculating there, that's the mass of ethanol, about 19.7 grams. Grams to moles, divide by 46.07, meaning we have about 0.428 moles of ethanol. Multiplied by Avogadro's number, we should have just over, or just under half a mole. So 2.579 times 10 to the 23. And then 2 carbon atoms per. So just less than Avogadro's number of C atoms. So it works out to be about 5.16 times 10 to the 23 carbon atoms. So answer E. Pentane is CH3. I think we know that there's going to be 5 carbons. The key is to have 4 bonds to each. We go CH3, then CH2, 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 then CH3. So we have 1, 2, 3, 4, 5 carbons, C5. That's where we get the penta from. And then 3 plus 3 on the ends and 2's on the middle works out to be equal to 12. So C5H12 is pentane. Reaction below gives us 2 quantities of the calcium carbide and water, or CaC2 and water. How much of the excess reactant remains after the reaction if the yield is 100%? Okay, so we could move to a BCA chart, but again, BCA chart, I'd have to kind of calculate the moles and stop. I'm probably going to use dimensional analysis on this step and just pick one of the reactants out and figure out how much of the other I need to react with it. And if I'm lucky, I can kind of address and answer the question with one calculation. If I don't choose correctly, I just need to run these numbers a second time. So I'm going to start with 22.5 grams of water and just say how much of the calcium carbide do I need to react with this quantity of water. Okay, because all I need to do is take 18.02 grams per mole of water. 2 moles of water that are present are required to react with every 1 mole of calcium carbide, and then 1 mole of the calcium carbide has a molar mass. It'll be 40.08 for the calcium, plus 12.01 times 2 is 64.10 grams. And so then I do 22.5 divided by 18.02. So we have about 1.25 moles of water present. And then we cut that in half because we only need half as much calcium carbide to react with that quantity. That's 0.624 moles. Multiply that by 64.1 grams per mole. That means, and says we need 40.0 grams of calcium carbide to react with this quantity of water. And then I look at my problem and I see I only have 22.5 grams of calcium carbide. So this isn't going to work. Okay, so calcium carbide is not the excess reactant. Water has to be the excess reactant. So we've just determined that water must be the excess reactant, and therefore it's not the limiting reactant. If it was the limiting reactant, it would have been totally consumed here down to 0, and then the calcium carbide given would have been less than the quantity that we have available, and then it would have been left over. So in other words, we just need to run this sort of calculation the other way around and say, okay, since we didn't pick right, and we just had a 50-50 chance, I just need to take the water and figure out how much mass of water is required to react with all of the calcium carbide. So 22.5 grams of calcium carbide. I use the molar mass of calcium carbide, 64.10 grams per mole of CaC2. And then I use that same coefficient just opposite, that for every 1 mole of calcium carbide that reacts, we need to have 2 moles of water present. And then every 1 mole of water has a molar mass of 18.02 grams. And so I go 22.5 divided by 64.1. Now this is only about 1/3 of a mole of calcium carbide. I double it in terms of water, what I need. So that means I need 0.702 moles of water to be present, and then I multiply by 18.02 grams per mole. So this isn't quite a mole, so this is a little bit less. It's 12.65 grams of water that we need to react here, and then we have 22.5 grams of water present. So water is the excess reactant. So water is the excess reactant. So the answer is A or D. And how much remains? Should be 22.5 minus 12.65 works out to 9.9 grams. Final question. Hydrogen predominantly exists as hydrogen 1, protium, hydrogen 2 named deuterium. Atomic weights of these isotopes are about 1.0078 and 2.014 respectively. What percent atoms in a natural occurring sample of hydrogen are deuterium? So what percentage of atoms in a natural occurring sample of hydrogen are the deuterium atoms? Okay, so the main idea here is that the average atomic weight that we get from the periodic table is equal to the fraction of the lighter times the atomic weight of the lighter plus the fraction of the heavier times the atomic weight of the heavier, and that this is equal to the average atomic weight for hydrogen is about 1.00794. And so you can see that the abundance is going to be much higher in the lighter isotope because we're just barely higher here in the average atomic weight of hydrogen. So the abundance of deuterium is going to be really low. So we can rule A, B, and D out. Okay, now our two choices are we can just plug this in here, plug 1 minus it in, or no, plug that in here, plug 1 minus that in for the fraction of the lighter isotope, and see if if C or E works out better for the answer. We can also set up an algebraic expression that we're trying to solve for. Like what we really want to find is the fraction of that heavier isotope. So the heavier isotope plus the lighter isotope have to equal 1. And so then the fraction of the heavier isotope would equal 1 minus the fraction of the lighter isotope. And so I can substitute, and that's actually not the clever substitution to make. The more clever one to calculate the quantity we want is the fraction of the lighter isotope would equal 1 minus the fraction of the heavier isotope. And so then we can substitute this in for a fraction of the lighter isotope here. So we can substitute that in. I don't know why I can't delete that. So I'm just going to change this to that. And then what we would have to do is plug the atomic weights in and then do some algebra and solve for the fraction of the heavier isotope. I'm just going to go ahead and hit stop, work through some of the algebra, then walk through it in a moment. Okay, so what I did was I cross-multiplied the lighter isotope mass into 1 minus the fraction of the heavier. So I get this expression here. I then subtract 1.00783 from both sides. So that works out to 0.00011. And then I do the algebra here to sort of combine negative 1.00783 plus 2.01410 times the fraction of the heavier to 1.00627 times the fraction of the heavier. And I divide both sides by the by that 1.00627 number, and then that gives me the fraction of the heavier is 0.000109. That's not one of the choices because the choices are percentages. So the fraction of the heavier times 100% would be the percent of the heavier. So the percent of the heavier isotope would be the fraction of the heavier times 100%. And so that's going to be 0.0109, but only 2 sig figs here, so 0.011%. So less than 0.01% of a natural sample of hydrogen is deuterium, according to this problem that we can work out using the average atomic weight of hydrogen. Now you could probably have guessed that just because the atomic weight is just a smidge higher than that of the lighter atomic weight isotope, so you can probably imagine that a good abundance, a good amount of the hydrogen would exist as hydrogen 1 or protium as opposed to deuterium. All right, that's all for this quiz. Thanks for the attention.